talking with Jenni Adams, an astrophysicist from the University of Canterbury. What is an astrophysicist?
Okay, well, astrophysicists want to study the physics of stuff out in space. So people sometimes ask me, about constellations and things. I don't really know any constellations because I'm more interested in actually how the stuff out there in the universe actually works. So for many astrophysicists, it's studying stars or galaxies, but for me it's actually the highest energy objects in space. So I'm going to draw about our project down in Antarctica, which is called IceCube. And IceCube is been built to detect neutrinos. And so I'm going to talk about the objects that we're trying to study and talk about why we want to study neutrinos from those objects. Okay, so we're trying to study the highest energy objects out in space. For example, there can be a black hole. I'll say this is a black hole, and around black holes there's these things called accretion disks. So that's all the matter that's actually kind of orbiting around the black hole. So not necessarily being sucked into a black hole, as they say, but just kind of orbiting around. Often you get these kind of jets coming out, which is matter that's kind of maybe starting to spiral in and then gets kind of kicked out. So that's we believe are the most energetic objects. We here on Earth, so this is Earth, this is not to scale. So this little thing down here is the Earth, and of course we want to observe all of this universe. And sometimes we detect these really high energy particles that come in, and we detect sometimes they're protons, there can be any kind of particles, and we have detected many really high energy particles. And we don't really know where they come from because these things are charged. I'll put a little, this means they have electric charge. And when you have an electrically charged particle, if there are any magnetic fields around, they just get twisted around in magnetic fields. So if they come in here like this, it doesn't actually tell us where they've come from, because in the meantime, from wherever they were created, they've gone on these kind of twisty paths. And so there's been a big mystery for about 100 years. We've detected really, really high energy charged particles that have come into us on Earth, but because of this business, we don't know where they come from. What was figured out was that wherever these guys were made, and say they're made in this object that I've got over here, there'll also be these other particles called neutrinos. This is the symbol for a neutrino. Neutrinos made, so if they meet some other proton and they crash into it, they'll make these neutrinos. So the good thing about neutrinos is they don't twist around. They've got no charge at all, so they'll just travel straight from wherever they were created. So this is them traveling maybe billions, maybe at least millions of years perhaps, through the universe, and they don't interact, and many of them will just travel on straight through our Earth and travel off, but every now and then one of them might interact. So we built a big detector at the South Pole. So here is the South Pole, and our detector is under the ground in the ice at the South Pole. And each of these little dots is actually a light detector. So here is the neutrino that did happen coming in, and it did happen to interact at this point. So if the neutrino didn't interact and just pass through, we wouldn't see it at all. You don't see neutrinos unless they interact. But if they interact, they produce some other particles that produce light. This is light from when the neutrino interacts. So we detect the light. So we wanted to use the ice because if you're going to look for something that produces light, then you have to have a medium, you have to have a detector that transmits light, has to be transparent. So we would say we could have had a really big block of glass, and we could have put our light sensors in the glass and waited for neutrinos to interact, then we'd see the light in our glass. But because the neutrinos interact so rarely, it doesn't happen very often, we need to actually have a kilometre by a kilometre by a kilometre of glass, but you can't get a kilometre by a kilometre of glass. Instead of making something man-made, we use the natural ice below the South Pole. And the reason really that it's at the South Pole is just so that we can have the ice below. It doesn't need to be at the bottom of the Earth really, it's just so that we can have a huge amount of ice. And the ice at the South Pole actually is really, really clear, so we can have our neutrinos interact, produce light that we then detect on our light sensors, and from this pattern of light we can work out the path that the neutrino has come from. And basically from the amount of light, so how many of our light sensors picked up the light, we can work out the energy of the neutrino as well. But there's lots of neutrinos coming from our sun. This is a star, but from our sun there's lots and lots of neutrinos, and there's actually 1 billion coming through your finger every second, all through any part of your body at any time, because neutrinos just can speed through the earth. And so there's loads of neutrinos around, but the ones from our sun are much, much lower energy than the ones that we're trying to get from these objects. So even when a neutrino from the sun interacts in our detector, it just doesn't create enough light for us to see it. So we need to see lots of our light sensors have to pick up the light for us to call it really an event. So the idea is that the neutrinos are going to be messengers from this high energy universe, these objects that do travel straight, aren't deflected, aren't absorbed. In fact, they're the only messenger that you can get directly for the very high energy universe. So we want to detect them. First we want to find out where they come from to solve this mystery of where these charged particles are coming from, and we want to know what energies they are so we can try to study these objects in detail and understand how these high energy objects are really creating all of these charged particles and these high energy particles. 5 years ago we discovered that we had neutrinos from astrophysical objects. This was the first time any telescope or any detector had actually detected neutrinos from outer space. But when we looked back to where these neutrinos were coming from, they didn't seem to line up with any objects that we knew. So for the last 5 years we've been trying to detect more of these neutrinos to see if we can get them to line up. And what we've been doing is sending out alerts. So every time we see a really high energy neutrino, which is actually only a few times a year that we see the highest energy ones, send out a message saying, hey, other telescopes out there, we've discovered a really high energy neutrino. And so those other telescopes can point their telescopes and look at where we've seen our high energy neutrino come from and see if they can see anything there. So these other telescopes, they looked and they did see that there was an object like this with a supermassive black hole. They're called AGN or blazars is another name. And they saw that our neutrino lined up with a blazar that happened to be flaring, so it was in its most energetic state in gamma rays at the same time as we saw our neutrino. So that was in September of 2017 that we found that this neutrino lined up. So now for the first time, we just published our results in the journal Science just in July of this year in 2018, and we found that this neutrino did line up with an object. So we now believe that we have found the first source of high energy astrophysical neutrinos, which was a particular blazar, and we have quite strong evidence, but not maybe at the real discovery level. Then we will have solved this 100-year mystery of whether these charged cosmic ray particles are coming from that travel on these tangled routes before they get to Earth.
Yeah. Why are we actually interested in studying neutrinos? Why do we build this mountain size?
$1 million, well, it's $280 million project. Physicists are always wanting to know how things work, and in different regimes. So one of them is the highest energies. We want to know how the highest energy processes work, how do they produce particles, what is really the physics at the highest energy. And so you might have heard mankind, is not something I work personally on, but have built accelerators, particle accelerators. The most famous one is in Switzerland. It's at a place called CERN, and it's a big ring under the ground, and it accelerates particles. So in that accelerator, we can accelerate particles to really great energies. But we've discovered that from these charged particles that we've detected, they're 1 million times more energetic than anything we have ever been able to create on Earth. So nature can make much higher energy things than we can. So if we really want to study the highest energy processes, we have to do the ones out in the universe. And as I talked about, neutrinos are only a direct messenger from the high energy universe.
Well, thank you so much for coming to talk to us on Science on a Napkin.
You're welcome.